Welcome to Industrial Applications Programmable Logic Controllers Level 2. In this video is the next in the series about manipulating data, and we'll focus on manipulating bits. In our last video, we looked at moving data and working at a macro level. Now we're going to look at working at the individual bit level. And this particular video is going to focus on toggling. There'll be another video on locking or forcing. And then we're going to look at moving instructions to change groups of bits at a given time. So toggling bits is a method that allows programmers to test a rung of logic by changing the state of a bit for one single scan. It is not particularly effective for manipulating data points during regular operation because the bit remains true for a single scan and may not be timed correctly to affect a change in the logic. So in this example, we're going to show you how to toggle a bit in software. So right now we want to get our power on, and I'm going to highlight the contact of interest, and I'm going to right click on it, and you'll see this is toggle bit. Now if you're one who remembers shortcut or hotkeys, Control T is another way to do it, and we'll toggle it once, and you'll notice that it only stayed on basically for a single scan. So the next scan that would have turned on the power on for a moment, but it would have turned off immediately because the next scan's not there. Some people attempt to use Control T by flashing it using their keyboard, if you can hear the sound of my keyboard going in the moment. But again, it's not necessarily an effective means of manipulating the data for a short period of time. It will work for a single scan if you're attempting to program something. Now where it is effective, if I'm going to go to another part of our program, I'm going to go offline for a moment and I'll show you where this is effective. Actually, I'll set that up and we'll do that in the next video. If a test bit is required during tryouts, or if an input has not yet been installed, the toggle bit can be a handy tool for temporary logic changes. So this is a quick demonstration of where the toggle bit can really be helpful for program testing during the testing phase. We have 3 rungs of logic here. So the second run, we'll focus on that for a moment. We have what is called a unconditional rung, where there is nothing preventing the output always on bit from being set. So because that rung has no preconditions, the output is turned on. It's always a 1 in the memory of the PLC. So anytime you use that output, that always on output, it's going to energize or fill in a spot that you require. That has advantages, but for the most part, you're not going to run into a situation where you're going to need to have an unconditional rung. And it also means that you're taking up 2 rungs of logic, and it's difficult to manipulate it to test for the off condition or state of that particular bit. So the alternative is to create a simple bit called test bit. And by toggling it, it's going to work in the same fashion as an unconditional bit because there's nothing else in the program that's going to turn that test bit off. Therefore, as long as it's been toggled on, it will stay on. However, unlike the always on bit, which I cannot turn off, this one I can again toggle it, and it will equally toggle on and off. So this gives you a way of inserting a test bit that you just want to check a branch of logic to see if you're on the right track, to see if it's going to work in your simulation. And when you find that it works, you can then remove that test bit or turn it off and on to observe how the logic behaves. And if it behaves the way you expect, you can then remove it. And some people will use a test bit if they have, say, a new input that's going to be installed in a particular operation, but the wiring hasn't been done and the logic hasn't been resolved yet, so they can put that as a placeholder. Normally, I personally would use an NOP, a NOP instruction as a placeholder as opposed to a test bit, but it does give you the ability to test the logic to see if it's actually performing the way you want to do. I/O locking, also known as forcing bits, is a method of temporarily overwriting the current state of an I/O bit during operation. It should only be performed by an experienced PLC programmer that is familiar with the operation of the logic or under the direct supervision of such a person. Warning: like all forms of data manipulation, great care should be employed when using the I/O locking function, as unintended machine motion may occur resulting in damage to equipment or operations and/or serious injury or death. The following are only suggested guidelines for using the I/O locking function of Connected Components Workbench software, and in no way should be considered a definitive list. Always follow applicable legislation, company safety policies, and good tradesperson common sense and practices. Failure to do so could lead to serious injury or death. 1. Never force or I/O lock any safety circuit or device. 2. Forcing or I/O locking should never defeat any motion, cycle, or machine cycle stopping logic. 3. Always have someone present that understands the equipment. 4. Always have one hand on an e-stop push button to halt operations in case of an emergency or unexpected operation. Five, determine if another method of solution can be employed. For example, repairing the defective device. 6. Notify all supervision and maintenance personnel of your intent. 7. Request permission to proceed. Do not proceed until granted. 8. Make sure the device you are going to manipulate is observable and will not impact other personnel or yourself. Due to the serious nature of I/O locking, there is no shortcut access to this feature. This is not an accidental operation, but a purposeful one. Begin by finding the I/O needed to be locked and then right-click on it to bring up the pop-up menu. Then click on Variable Monitoring. In our last video, we talked about the 3 different rules regarding locking and operational behavior of locking. We're going to go a little bit further in depth. We're going to look at Rule 1, that you can only lock a physical I/O. Rule 2, that locked inputs are scanned into the operational logic, whereas Rule 3 says locked outputs are set. There's slight variations in a theme, but it's important to understand how they operate, so we're going to dive into a little bit deeper. Okay, in our last video we went through the procedure to actually lock and unlock bits, and I'm just going to reactivate our simulator here. And what we noticed was that you could lock an output, but the output appeared to be changing state on the screen, although it wasn't physically changing state. It's an operational procedure we're going to look at in the third part of this series. The other thing is, we talked about the very first rule was we could only lock physical real-world I/O. So in this particular run, we can see that my outputs are actual real-world outputs, and we have a series of sequence bits that are triggering the outputs that I want to come on depending on the sequence I've selected. So let's take a look at sequence bits. Now, when we talk about manipulating bits, we also tend to think of dints and ints and synts, etc., as being homogeneous and a single data type. As in, if I have a value of 32,768 positive, it's got to be in a dint, and that's just a decimal number represented by a stream of bits. We can also use the bits individually, and that means we're allowed to manipulate them. There's a couple things we're going to go through on this that I want you to pay attention to. So I created a dint called sequence bits, but then there is a period after sequence bits followed by a 0. And when I did that in my program, the software understood that, oh, I'm not looking at this in terms of a unit, but I'm looking at it in terms of individual bits. So once I've done that, it knows to break it open for me when I want to examine the individual bits. So there's all my 32 bits. Right now they're all off. And if I look over on my lock column, because these are internal bits, I cannot lock them in place. Now, if I elect, if I want to start off with a particular set of lights turned on, I can set an initial value, but I cannot lock an internal variable. You cannot, if I were to open up, let's see if we can find a timer here. There it is as a 32 bits, forward reversed. Let's keep a look on this. I can lock on my internal system bits because they are actually controllable. And they put outputs, those are real world. As long as it says lock, I can do it. Okay, let's change my scope, find a sequencer bits. Nope. Okay, let's go look at another program. I want to find a timer, and I believe that's in my sequence cycle. I have a couple move statements, a TNOV, and a count up and down. So let's do the same thing. Let's go into our local variables, and here they're giving me a lock, but I can't click on it. I cannot manipulate any of my count up bits. So in most situations, you're not going to ever need to manipulate and lock on an internal bit. If you do, you'll have to do it in logic. And there's a number of ways that you can do that. To permanently turn something off, take a unconditional run, turn an output on, then use the not bit in front of it, and then that internal output's never turned on. There's a number of ways you can do it in logic. But these are conscious decisions that you want to do, and internal bits are controlled and are the purview of the software, of the logic running in the, we can only control inputs and outputs. So that's the first rule. Only real world inputs and outputs can be directly locked. Okay, we're going to look at Rule 2, which says that if I force on or lock on an input, that it will logically flow through the program and operate through the program. So I have two simple rungs that I'm going to demonstrate this principle. And the first one has got an input, digital input 25, which I have on my simulator. If I turn on input 25, it turns on my internal bit called prove it 1. Okay, so I've toggled it on my software the same as if it was flagged, if it was a proc or something, and it would turn that on. So what I'm going to do is I'm going to right click variable monitor it, and I'm going to lock it in the ON position, and now you'll see that it's locked and my prove it 1 is turned on. So that tells me that when I force on an input, it turns and solves the logic. So let's try something different. What I'm going to do is I have input digital output 0, 1, and I'm going to try it, and this is rule number 3, that digital when you lock on outputs, they don't resolve in the logic. So let's take a look at that. We're going to move this down to our digital outputs, and we're going to turn on our first digital output. Now I'm doing all this again when it comes to locking. It's not something you do as a habit. It's because you're kind of backed into a corner. In this environment, I know that there's nothing moving, that's all simulated. I don't have to take extra precautions, but that's not a mindset you should develop. You should develop a mindset, especially when it comes to forcing, because it's instantaneous. Once you hit that lock, it takes into effect. You can't take it back. You can turn it off really quickly, but if you don't understand the process and you force something on, or if you force on an input that it should not be on at a given instance, you can cause a lot of damage and quite possibly hurt yourself and somebody else, and I can't stress that enough. But at any rate, okay, so we're going to force this output. In this case, I don't go to the logical value, I go to the physical value. I click my lock, I click my physical value, and down on my program you can see I have a lock, but the associated contact with that output is not high. The physical output that I have turned on, I've said okay, turn that on, but the processor doesn't see it. So we're going to look at why this is. Why do we have this conundrum where if I force or lock on an input, the logic gets resolved, as it's shown in rung 2 here. But if I do the same with an output, it doesn't resolve. So we're going to look at that. And being a good practice, since I'm not going to be monitoring this, I'm going to remove my locks and let the logic do what it's got to do. There should be a fourth rule I'm going to add: never walk away from a locked bit. If you've got something locked on or locked off, for whatever the case may be, you babysit it until such time as you can make an effective proper repair. Alright, so we're going to look at the way the processor works. Now this is, we call this the broken circle. It's not applicable to all PLCs, but it's a good basic working model to understand what the processor does and how it actually resolves logic. So the first thing it does is it does a little bit of housekeeping. Turns up, makes sure everything's good, there's no faults. Then it reads all of the inputs, the physical real-world inputs that are connected to it. And it determines its status, whether they're high or low, and it starts to solve the logic. Now as it goes through, it doesn't set the output right away, because in this instance it may be high. In this case might be a identical or a different rung that has the same output, and now it's low, might be high again, etc. But we're going to assume, just for simplicity's sake, We know that the last order wins, but we're going to say that these two are high, and we're going to check it. Yep, still the same, no change, no change. Get to the end, and the last thing it does, it turns on the output. It goes and does this, the next scan, does the exact same thing. It reads the inputs, doesn't care what happened the last time. Things change out in the real world, looks at the inputs, starts to solve the logic, and then finally sets the output again. But things change once we start using forcing. So when we go to force, it's not exactly that the inputs have changed, it's the way it's interpreted. So this output here, say it's a defective proximity switch, but you have to run, you've got to keep going until lunchtime until you can lock everything out and fix it. Okay, so it's a temporary measure, you know exactly what's going on, it's perfectly safe, nothing's going to get damaged, and you've been given permission to do it. So you go in and you say, okay, I'm going to force on my input. So now, as it reads its inputs, it says, oh, okay, I know this input in particular is on, and all the way through the scan, it keeps seeing a 1. Yep, and finally at the end, it still sees it as true because you've told it to. It sets the output and carries on. On the next scan, it checks, oh, I still have a force, turn that on, and it carries on all the way through. So with an input, when you force it on, it alters the way the logic is scanned. It sees that as being a true bit even though the physical real world device is not. Outputs, however, do not operate the same. So let's say that we have to force on an output, and this is the contact that the output's forced on from somewhere else. Because of the way the scan works, it looks at the inputs and resolves the logic. It does not see the force. It carries on, that's off, that's off, that's off, that's off, and then the last part it goes, oh, I've got to turn this on. So it turns on the output. But the logic behind it does not support it, it's just that we've turned the output on. To look at this a slightly different way, let's kind of pretend we're looking at the actual physical wires and working in the PLC. So here's my input sides, we're feeding it with 24 volts, and this is my output side. So the red wires are 24 volts going in, and the return is all on the black. Normally we sync our inputs and source our outputs. So the 24 volts goes to my first switch. My first switch is open, so I don't have, my contact's not true, I don't resolve the logic, I don't turn on my output. Straightforward. On the second one, my switch is closed, so that puts a voltage at my terminal screw. It sees it, says great, I got voltage. My logic says to turn on this output, and we close an internal triac that supplies the 24 volts, sends it out the terminal screw, and we turn on the light, and it works. Perfect. On our third one, we had a defective switch, so somebody said, you know what, I'm just going to put a jumper wire out at the switch. So they locked it all out, they put the jumper wire in, turned it back on, and lo and behold, the PLC sees the voltage there. It says, okay, that's true. I'm going to turn on my output because my logic's solved. Turn on the output, and the output gets energized. Perfect. The last switch, the switch is left open. Now somebody did some forcing before and wasn't paying attention, didn't delete them, doesn't matter, it's behaving differently. So as far as the logic's concerned, that is not true. This is off. I do not have continuity, therefore my output is not going to be turned on. But maybe someone was industrious and they went to the 24 volt supply and they ran a wire, put it on the terminal screw, bypassing the internal switching, and turned on my output. The PLC has no idea that a jumper's been put on the outside. So it's not going to resolve this. As far as it's concerned, it's still examining the condition of this switch. If that switch is open, it's not going to turn this on. Therefore, the output on our program is not turned on, but we've locked it on, and only the output, the physical output, is energized. Any associated contacts with that output will still be low in the logic. It's important to grasp that concept when it comes to forcing and locking on bits. There are a lot of people who still, that I've worked with for many years, they would still think if you forced on an output, it would change all the logic interior, and they would look at it and they would forget, and they would not see that it's on, and they're going, I don't understand what's happening, and the output's left on. The other thing that can happen is that you can force on an output, forget about it, and you look at the logic trying to figure out why your machine's not running right. Oh, that's the output's forced on, but that doesn't make sense. The logic's turned off, but it's been forced on. I forgot it's got the lock on it. Yeah, better take the lock off. Now it's behaving properly. So it's really important when you're working with forcing to understand the difference between the inputs and the outputs, and the fact that you can't do internals, you can only do real physical world, and that inputs, once you force on an input, it's resolved in the logic. When you force on an output, it is not resolved in the logic. It's like literally running the jumper wire on the outside to bypass the PLC. The PLC will not resolve it in logic.